I'm going to use a microphone, not because you won't hear me, but because of the camera. So first of all, welcome. There may be some other people joining us. It always happens. But we're going to start, right? I would like to start with introducing myself and my background. So I live in the United States. I work at a community college, and my work is related to teachers. So I work with teachers entirely, kindergarten to high school, to help them implement new standards that we have in the United States. My education and my growing up was not in the United States. I grew up in the Netherlands, so in Europe, and I studied astronomy, and I actually worked as a researcher for 15 years. So if you join us, just come sit in the front because that's much easier. Thank you. The topic today is very important for astronomers because they deal with energy and matter, but not just astronomers. Every scientist deals with energy and matter. So that's why we call it a cross-cutting concept. So I want to talk a little bit about where this comes from today, and then we go deeper into energy and matter and how you can help your students see what the difference is between energy and matter so they don't confuse the two. But before we do that, I would like to get an idea of who is in the room. So raise your hand if you're a teacher. Okay, right? So okay, everybody's a teacher. Anybody teaches children ages 5 to 8? Yeah. 9 to 12. Okay. 13 to 15. Some of you teaches children many different ages, right? And then 16 to 18, right? So all of them have to learn about matter and energy, but the level at which they have to learn about it varies. So great. So welcome. So now I have to make sure I push the right buttons here. I think it's this one. Okay. So the ideas that I'm presenting here are part of new standards that were developed in the United States. And the focus of these standards is to move away from focusing just on content and memorization of content, but having students apply the information. So it's really about application. And these standards were very well researched. We know a lot about how students learn science, and all that research over the last decades have been incorporated in these new standards. It also takes into account what students should be able to do in the 21st century to get jobs and to be competitive. So that's all included in here. And the main idea, just to sort of give you a little bit of the background, is that we need to move away from just focusing on what we call disciplinary ideas. So knowledge in physics or chemistry or biology is not the only thing they need to learn in science class. They also need to learn about ideas that cross the different subjects, which are the cross-cutting concepts. And energy and matter is an example of that. And most importantly, they have to be able to apply those ideas, and they can do that through practices. And even though the focus is not on practices today, you will engage in practices. But things like asking questions, planning an investigation, developing a model, and so on. Engaging in argument. So today we're going to we'll focus on the cross-cutting concepts, and these are the cross-cutting concepts. So there are 7 different cross-cutting concepts, and take a moment to look at these. Patterns, cause and effect. You can read the list. These are big ideas that can be used in physics, in chemistry, in biology, in earth science, in astronomy. And yesterday I did a workshop on systems and system models. And today I'm going to focus on energy and matter. Now, these concepts are not new. I mean, you've heard about these, I'm sure. So they're not new, but the way we want to use them, I think, is new. We want to use them to give students a different lens to look at the world. And different lenses allow you to go much deeper into the content, and that's what we want to do. But to do this, we have to make them explicit. That is, we really have to talk about these cross-cutting concepts in a very specific and explicit way. And we're going to do that for energy and matter. So now it's going to be very interactive. So I'm going to be talking to you. I'm going to have you apply these ideas. So what do you know? Talk to the person at your table. What rules do you know about the flow of energy and matter in systems? So what rules do you know? When you have energy and matter in systems, what rules do they follow? Talk to the person next to you. Okay, so you had a moment to discuss this. So what do you know? Well, let's start talking about systems. We talked about systems before, and some of you attended that workshop. But what is a system? Who can? Yeah.
A system is a set of components. They interact with each other.
So, excellent. So a system is a set of components, and these components interact. And how many components do you need to have a system? At least two, right? And if you have one, there's no interaction, and then actually also there's nothing you can observe. So in science, we're always dealing with at least two components, usually many, many more. So everything in the universe is really a system. And we think about the interactions between this system, and in those systems, there is energy and matter that sits somewhere, and sometimes it moves from one place to the other or from one form to the other. So what do we know about those flows of energy and matter? What rules do they follow? Does anybody want to share what you talked about? Yeah?
So what I'm going to say, we discussed it through an example. We were saying that the food chain is a system. And basically what we know about energy is the law of conservation of energy, where it cannot be created. You all know it. But here, you need, the matter moves in throughout the food chain, and the more it moves, the more energy is created and the less matter is there. So eventually matter is transformed into energy.
So we're going to talk about that. But so you mentioned the food chain, and we're actually going to do an example about the food chain later. So, but one of the first things you said is energy is conserved, right? In a system, energy is conserved in a system. So that's one of those rules. Is there another rule, or somebody knows something about matter?
About the kinetic energy and the solid state, liquid state, and gaseous state. That the particles that have a more force of attraction in the solid state, so it has the least kinetic energy.
So we have matter has different states, and we can go from one state to the other, and that energy is required or subtracted when we go from one state to the other. Is another rule about energy and matter?
In order to have a transfer in mass and energy, in matter and energy, you need to have some potential difference, or difference in concentration, or difference in temperature. So this difference. It is the driving force for transfer of matter and energy.
So there is a difference between matter and energy, and we mentioned that energy is conserved. What about matter? Is matter conserved? Okay, both are conserved. So those. We're going to focus on those two. So in a closed system, matter and energy is conserved. What do we mean with a closed system?
I think it's isolated from the surrounding around it.
Yeah, so yesterday when we talked about yesterday when we talked about systems, we mentioned that in a system we need to think about the boundary in the system. And we actually had an activity with with water and an ice cube, and we determined what is the boundary of this system. Is it the entire universe, or is it the Earth? And then we decided it's probably just a room, right? So if you just take the room and we keep the door closed and make the windows perfectly isolated, then within this room, matter and energy should be conserved. And we do this in science all the time. We define the system, and then within the system, As long as it's a closed system, then and nothing can go in and out, then matter and energy are conserved. However, and I'll come to you in a second, I saw your hand. However, the assumption that the system is closed is often not true, because we want to simplify things, so we make the system as small as possible, and then often we have to worry about energy and matter coming in the system and going out of the system. Even assuming that this room is a closed system is really not true, because actually you moved from that table to this table because the sun was bothering you, which meant there's actually energy coming into this room from the outside, right? So, so that's something we have to keep in mind. You wanted to add something?
I would talk. This system is a closed system. Contains a solid state, liquid state, and a gaseous state, which is an equilibrium. When the rate of evaporation equals the rate of condensation, so you reach the equilibrium. The concentration of both reactants and the products, so it is the liquid and the gas, reach at a constant rate. This is a system.
So I agree with you. I partly agree with you, and I partly disagree with you. So I agree with you in terms of matter, but what... Okay.
I think by time it will change the contents and the ingredients inside it, and this indication that it's not a closed one. I think it's an open system, but it needs some time. Maybe there's a no matter change or exchange. Maybe there's an energy change or exchange. Yes.
So matter.
Yes. Conserve. Yes. No, it's not. Yes.
So these are some of the discussions we have to have with our students to talk about open and closed systems. So in an open system, we have to think about the matter going in and out of the system as well. Now, here's the problem with students. Students learn that matter and energy are conserved. And you learn that too. But what students often do is they use it when it's convenient for them. They don't use it as a rule. And what do we mean with a rule? Here's an example. So what's wrong with it? It's in English, but what's wrong with this sentence? Yeah, there's a rule that's broken, right? So there's a grammar rule broken. So we know that in language. So now let's look at a science example. What's wrong with this sentence? What's wrong with this?
It's respiration that converts O2.
So the problem with that sentence, if you look at it, is where does the carbon come from, right? So breathing converts O2 to CO2, but it doesn't make any statement about the carbon. You cannot convert O2 to CO2, right? So it's partly language, but this language is important because it doesn't really account for the carbon, right? Well, you can change the wording, but yeah. Right. But there's somewhere where the carbon comes from, and that has to be in the sentence, right? So the first one is easy, but the second sentence becomes a little harder. Now, we can talk about this forever, but the best thing to do for us is to do an example and apply this idea, and then we can see how easy or how difficult it is. So what I want to do is a very simple example. So science does not have to be hard. So sometimes you go to the people on the floor and they want to sell you expensive equipment, but you could do science in a very easy way. And I just brought some matches. And I'll demonstrate it and then you can try it. I am just going to light a match. Okay? And observe what happens. Now I'm going to have you do this. And what I want you to do is, I'm going to give you matches to play with. Usually you don't get that in school, right? So, and if you can just sort of share so that everybody can observe, right? And then the four of you. I know. No, I always bring the wrong materials when the Queen visits. Last time I did a workshop, I had batteries and wires and acids. So it was, yes. Nobody checked. It was in this bag. It was all hidden. So what I want you to do is I want you to light a match. Don't burn yourself. don't set this place on fire. And really carefully observe what you see when you burn this match, because we need these observations. So do this, and maybe do it more than once. So focus on observations. I don't ask you to explain it. What do you observe? So I want to add something here. This is very difficult for students and for adults. We do this all the time. We always want to explain before we make careful observations. There's a difference between observation and explanation. Observation, we can usually agree on what we observe, although some people are better observers than others. We may not agree on what the cause is for the observation or what the explanation is. Right now, we're not focusing on any explanation. I haven't even asked you what you want to explain. I just want you to observe everything you can observe, including, think about different senses as well, right? It's not just vision that you have. So did everybody do this? Did everybody make your observation? So Ahmed, can I ask you to write? So what I want to do is I want to share these observations, because these observations we're going to need in the next step when we're going to apply these laws of conservation. But we want to make sure that everybody agrees on what we observed. So I'm going to ask each one to add one observation. So I'll start with you. So give me one of your observations.
New matter is produced. And you...
That's not an observation, that's an interpretation. Give me something that you actually observed. Okay.
Blue flame.
So Dave took your turn. You still get this. You smell something, right?
Blue flame, red flame.
So you saw a blue and a yellow flame. Okay. So you saw light. You saw light coming off. Okay, great. Yeah. Heat. You felt.
Yes. Heat.
Right? Yeah. Heat. You felt heat coming from the.
It seemed that the black stuff is less than the original as a quantity than the original. That's my observation.
Okay, so when it turned black, it seems like seems like less material there in the stick, right? Okay, all right. Anything else you observed? Nothing. Who has something to add to this observation?
Smaller and smaller until it vanishes.
Okay. So the flame, as it burned, the flame became smaller and smaller, and then it vanished. Anything else? Hold on. I'm going to go. Give everybody a chance.
I noticed observed it produced smoke.
It produced smoke. All right. So it produced this, fuzzy, fog, smoke. We call it smoke. Anything else? So there's a lot of things we can observe by just looking at a match.
The color of the match converts from white to black.
So the color of the match changes from like white, in this case, to black. Anything else? Sorry? The match bent. So was it just the black stuff? Is it just as strong as the white stuff? So it's brittle, right? Okay. What?
Change design of material.
So it changed the properties of the material. Okay, good. So we have a whole bunch of observations here, right? So we smell, the color changed. We had a flame, so we saw light, right? The match actually became brittle. We felt heat. There was less material after the burning, and so on. Okay, good. So now I have some questions for you to think about. I have these questions. Now this I want you to do individually. This is not working with a partner. I want on your observations and thinking about the rules about matter and energy. Thank you. So I ask you to, there's five statements, and for each statement I want you to indicate if it is false or true. You don't have to write why right now, we come to the why later, but is it false or is it true, each of these statements? Based on your based on your observations, and also you can bring in your own knowledge, because observations alone are never enough. Yeah. So you bring in, for example, what you understand about matter and energy. Yeah. The question is, what do I mean with destroyed? Is that when it destroyed means it was there in the beginning and it's not there anymore afterwards. It's not, yeah, it doesn't exist in that form. Right. So if I say the wood is destroyed, it means afterwards there is no, that's not wood anymore. Right. That's what it means. So did everybody finish, or is still working on it? Everybody finished? Okay, so what I want to do is put the sheets together. Take those sheets, put them together. What I'm gonna do is, if you give your sheets to that table, you give your sheets to this table, just pass them, okay? There. Yeah, give it to them. Right. These two sheets go here. Yeah. Yeah. So we give this to you. Sorry? Are you finished? Yeah. So, no, put it here. Okay, and then this goes there. So everybody gets somebody else's answer. Everybody should have somebody else's answer, right? No, you're gonna get this. He's helping me here. So the reason I do this is that I actually want to get a sense, and I want to give you an idea of what the group thinks. You have two more? There. Okay. So we want to get a sense of what the whole group thinks. But if I ask you to report your answer, and you're probably very honest, but students, they often look around and then they go with the majority. So now, because you're looking at somebody else's answer, you're going to be honest because it's not your answer, right? And I'm going to put this on the slide. And luckily, we don't have too big of a group, so we can do this. So, first question: How many of you on your sheet? This is not the answer you gave, but what is on your sheet? How many has that this is true? Yeah, on that sheet, right? Yeah. How many? Raise your hand if it said true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 said true. And then how many said it's false? You want to do that? Yeah, thank you. How many said it's false? 1, 2, 3. 3 people said it's false. Okay. Right. So what about 3 people said it's false. So what about number 2? How many people said the wood of the match is destroyed when it burns is true? How many? 1. Yeah, how many said it's true? That it is 1, 2, 3, 4, 5, 6, 7, 8, okay? And how many of your sheets say that it is false? That should be 14, should be 6, right? 6. For yes? Yeah. Number 3, the molecules of the wood are destroyed when it burns. How many say this is true? No. Somebody, you have to make a choice. So 1, 2, 3, 4, 5, 6, 7. Okay? So 7, and then should be 7 on the other side. It's just a rough idea, right? Number 4, how many say that was true? How many sheets? 1? No? 1, 2, 2? 3? 3? So 3 and 11? 4? Oh, it meant 2. 2. Okay, so 2 and 12. And then the last one. How many say that this is true? 1, 2, 3, 3. So 3 and 11. Okay, so as you can see, and this is what you normally would see in a classroom, you can see that there is some disagreement, right? So we don't all agree, even though we have the same observations and we know the same rules about matter and energy, the way we apply it in our thinking is different. And so this actually was done at a teleconference and a webinar from the National Science Teacher Association with, I think, 200 educators. And basically the responses, these are all science teachers. The responses were 50-50. Half of them thought it was correct and the other half thought it was false. So this is something that not just students struggle with, like teachers struggle with this interpretation. So what I want you to do now is I want you to discuss the statements with your table group and present an argument, make a claim to why your answer is correct based on your knowledge and the data that we observed. Okay? So talk to your partners. So some of you had false and some of you had true. So can you convince each other based on evidence and based on your interpretation of the laws of conservation? All right, so you had an opportunity to talk about these with your partner. So let's talk about them again. Let me go back. So now some of this may seem like semantics. In other words, what does the word means here? And this is in English, so I know it can be a little harder because it's not your original language. It's not my original language either. I speak, my original language is Dutch. But what the first sentence says is that matter, the wood is converted to heat. In other words, matter is converted to energy. Does that happen? Is that actually happening? Is matter actually converted into energy, or is something else taking place? So what do we think?
Heat and light is a shape of energy.
Okay, so you're saying matter changes to energy. Does anybody else have a different idea about this?
Perhaps when the matter is changing state or form, it's releasing energy.
So there is some. Are you saying that in the matter is energy? Energy is stored in a certain way, and that is being released. Okay, so that's different. So anybody else want to? You want to add something?
It's chemical energy. Yes.
Tell me more about it.
So I mean, it's things related to the electrons, shell electrons reacting with each other between different atoms. That's what's happening, and the net result, yes, there is energy released, and if we take it as masses, if we apply E equals mc squared, then there is a very minute change, but it's not that big. Yani chemically, we cannot measure it in the lab. if you want to be very precise. But that's in principle what's happening.
So there is, what you're saying is that there is energy, right, inside the match that stored in the bonds, and those are broken, and that energy is converted in a different type of energy, which we can actually see as light and heat. We see both parts of the spectrum. So the confusing thing is that we all know about this equation E is mc squared. Like mass can be converted in energy, but that almost never happens. It happens. It happens in nuclear reactions, but it doesn't happen. Yeah. But it happens, for example, in the sun. So in the sun, we have hydrogen, and when we take 4 hydrogens, we make helium, and then if you look at the periodic table, you can see there's a difference in mass. Some of that mass is actually lost, and that is converted into energy. But when you burn a match, that's not the case. What is the case there is that the energy that's stored in the wood is being converted. So energy stays energy, and mass stays mass. And we're going to come back to this because this is challenging for students. What about the second one? The wood of the match is destroyed. In other words, if you look at the black piece part that is left, is that still wood or is that no longer wood? So what do you...
I think it's a new material. It's carbon, maybe, because
It's a new material.
yes.
And what's your evidence for that?
And the new color and the more brittle, the texture of the material has changed.
So different
Properties.
different properties. Now, what change has happened to the match? What kind of change is this? Is this a physical change or a chemical change? And what's your evidence for chemical change? Heat? What else? Light? You cannot return to the previous, so you cannot go back from the black into... If you could do that, then you're a magician. But you cannot easily go back, right? What else? Any other new substances were formed because they're black? And then there is the smoke too. So that's also evidence of some substances, yeah? And there's energy released, right? So we have multiple indicators that suggest that it's a chemical change. Okay, so what does that mean? So that means that the wood of the match is actually destroyed. The wood isn't there anymore. So what happened to the molecules in the match? Are they destroyed? Are these molecules still there? No. Because in a chemical reaction, that's the definition. In a chemical reaction, what happens to the molecules? They change, right? So I gave this example yesterday or 2 days ago. Chemistry is really simple. It's like the school dance. And I asked the educators in the room, and I said, do you have school dances at your schools? And people said, no, not here. But in the US, we have school dances. Like boys and girls, they meet at the school, and there's music, and they dance. So boys and girls dance together. And then at some point, they switch pairs. And that's a chemical reaction, right? So you have a boy and a girl, that's a molecule, and then you have a different molecule. So that is similar. That's a model for what a chemical reaction is. So the molecules are destroyed. What about the atoms? The atoms are not destroyed. The atoms are there, right? So, because if you destroy the atoms, then you're getting into nuclear reactions. So you didn't destroy the atoms. And what about the matter, the mass of the wood? The mass of the wood? Right. So the mass, we notice the match weighs less, but if we capture all the gases that come off and we weigh it all precisely, which you can do in school, don't try that, but then the mass is conserved. So now that we notice, look at these 4 statements and talk about these statements. The first one is similar to the one that we just discussed, but there's some other statements that we often use in daily language that confuses matter and energy. So how would you change these statements to make this into a statement that's just about matter or just about energy, right? So talk with a partner about this. So exercise helps us lose weight by burning off fat as energy. How would you say it differently? So talk to a partner about it, and all of them. Okay, so these are just some statements for you and for students to think about. The first one we talked about, so we don't need to discuss that. But what about exercise? So exercise helps us lose weight by burning off fat as energy. And we see this everywhere, you know. And so fat is burned and turns into energy. So that's not a correct statement. So what is the correct statement? How would you change that into a more correct statement? Yeah. You want to, yeah?
It converts to other materials, not to energy.
Okay, so the fat gets converted into other materials. You can talk about what that is.
Yes.
And what happens to the energy?
I think there is an potential energy in the body.
So there is energy stored in fat is actually now converted into other energy.
Yes.
So, actually, it turns out that a lot of people who want to help you with weight loss actually doesn't know this. So they don't know the separation between mass and energy. Do you know how, if you want to lose weight, right? How do you actually lose that matter? In what form is that matter actually, does that matter leave your body? Does anybody know? And what So the matter actually leaves your body as carbon dioxide, mostly, and water, but 90% carbon dioxide. It's mostly carbon dioxide, yeah. And so to lose weight, actually, you need to breathe a lot. You get rid of your carbon dioxide. It's the opposite of what happens to plants. Well, so again. It's the opposite, and you can think about that in the next example that we use. So So what happens when we lose mass or lose weight is that matter is actually leaving the body as carbon dioxide and water, and the energy is converted. The energy in our fat is being converted, but that is not converted into matter. It's converted in other types of energy. Okay, and then cellular respiration converts glucose to ATP. And we talked about, so does glucose change into ATP or something else? Yeah.
It's changed into water and carbon dioxide. The energy in the bonds in the glucose molecules will change.
So none of the matter that is actually in the glucose goes into the ATP, but the energy that was stored in the glucose now is being stored in the ATP molecule. So again, it's an important distinction that students need to understand. The last one, gasoline is converted to kinetic energy of a moving car. No. So where's the energy going? The chemical energy, right? That is converted to. And so what happens to the matter? So the gas, so if I put gas in my tank, at the end, there's no gas. So the matter is gone too. Where does it go? And what is that substance? Carbon dioxide, carbon monoxide. So that's why we have the problem with, global warming, right? Because those pieces go into the atmosphere. So this is not easy to keep these things separate, because in our language, we're sloppy, and we hear this language, and then we confuse matter and energy. So we need to keep that separate. So what is really important for students is that when students observe change, they need to figure out first, is the change physical or or is it a physical change or is it a chemical change? And that's why I had to make you these observations. These observations suggested that the change is a chemical change. Because when we say matter is conserved, we don't specify what matter is conserved. You don't know what matter is conserved. So you need to know the change. So if the change is physical, then the mass, the substances, the molecules, and the atoms are all conserved, but the volume is not. So molecules are conserved in a physical change, but in a chemical change, only the mass and the atoms are conserved, but the volume, the substances, and the molecules are not conserved. So when we use these conservation rules, we have to think about what is the type of change we're looking at. And again, we need to give students examples like the one with the match to get them to think about this. It's not a question of lecturing to them. So I want to move to a different example of energy and matter. And I want to talk a little bit more about a system, because we're going to talk about ecosystems. So a system is a collection of components, and somebody already mentioned that, so that's great. A system has a boundary. So in other words, to simplify things, we put a boundary around it. So in case of an ecosystem, we may decide that, you know, these fields are the ecosystem, and then everything outside we don't include. And we have to decide, or the students have to decide, where's the boundary of the system? And then within that boundary, there are components. There are parts of the system that are important that we want to include. And then we need to think about how these components interact. So how do they interact? What are the flows? How is matter and how is energy moving through the system? And this is particularly important if we talk about ecological systems. So we're going to do an example. So I'm going to give you a really simple ecosystem. So there's 3 parts. There's rabbits, there's grass, and there's foxes. Right? So I don't have to tell you who eats who, so you can figure this out. Okay, good. But what I want you to do is, and now we're getting into a practice, right? So I want you to develop a model that represents this ecosystem and that illustrates, that shows the flow of the matter and the energy. So where's the matter coming in? Where's the energy coming in? And how is that going through the ecosystem? And are there places where it leaves the ecosystem? That's for you to determine. To help you think about what's the boundary, so what should be included in the ecosystem. I'm not going to give anything away, but you need to think about, so what are the sources of energy? What are the most important components? What are the interactions? And then what are some ways we can represent the matter and the energy? You have on your table a piece of paper, and you have a marker, so you can draw. Right? If you need more space, I can give you another piece of paper. But I want you to try this. And you already know quite a bit. You use any knowledge you have about ecosystems. So you're doing it for this particular ecosystem, not just any ecosystem, this specific one. So the grass, the foxes, the rabbits. So some of you will be making excellent progress. And you're teachers, so many of you, you teach this or you have thought about this. I want to give you an opportunity to look at each other's models, because we all have different ways to represent it with different details. So what I invite you to do is to get up from your seat, walk around to the tables, and engage in a discussion with each other about the different models that were drawn. So this is an opportunity for you to get up, look at each other's models. Okay, so you had an opportunity to look. I actually wanted to ask this group if you could bring your example, or maybe even better, if you're willing to do this, could you start over and sort of share your thinking here with everybody? And why don't we move this over here, because everybody's here. We can help you. Okay. All right. So And then please ask questions, or you know, if you disagree, please. Okay, go ahead. I'm going to give you the microphone.
In this model, we draw the food chain. In all food chains, they must start with the producers or the grass, because producers, they can capture sunlight or use light energy to produce food, their own food, in photosynthesis. The main source of energy here is the sun. I'm going to draw.
You're going to draw, and I'm going to explain. All right. I'll explain while my colleague draws. Basically, the grass is going to capture the light energy from the sun in order to convert it into... Sorry. هدول مش شغالين. منظر. شو اسمه? In order to convert it into glucose. Now, basically, we're talking about now the matter and how it flows. Glucose is going to be, rabbits will eat the grass, and the glucose is going to be converted, the matter of glucose will be converted into carbon dioxide and waste products, water, and in respirations, it will, you know, we will have energy. And then, you know, it will flow into the fox. But our main concern here was the rabbit, because it's the rabbit, it revolves around the rabbit. So this is the matter flow. And as for the energy, here, would you like to explain?
The arrows here in all food chains, arrows represent the flow of energy and matter between living things. Energy coming from the sun will be transferred from the grass to the rabbit to the fox. We use energy to produce glucose. From where we get glucose? From another matter, from carbon dioxide, from water. Energy will be used to combine carbon dioxide and water to form a new matter. Chemical change. New matter. We have to make new bonds between. We use energy. Okay. Glucose. Grass will use glucose. The extra glucose will be stored in grass. When rabbits eat grass, they will get 10% of the matter. 10%. So every time matter is transferred from one organism to another, only 10% will be transferred. Rabbit will get glucose or starch. This starch will be used again in respiration to produce carbon dioxide and water. The energy from glucose will be transferred to another forms of energy, which rabbit will use kinetic energy and heat energy. Then the extra glucose or starch in rabbit will be stored as fat. When fox eats, the rabbit will get 10% of this matter.
So I can see that your chain has finished on the fox and the energy has stopped there. Yes. So it's continuous process. Have we? Oh, it's okay.
Between the two. So,
Can I pause for a moment? When you were in the classroom, this is what you want, the conversation between you.
Yes. Relax, enjoy it. Okay, so you said that the fox is eaten by something else.
Yes.
I don't know that there are creatures who eat foxes.
If there is.
But I think not. I think it's unlikely that fox
if there
finally
is
is
another
as
organism
a predator.
Yes.
Maybe, yeah, probably.
I don't
but
think
usually,
it's the top
I don't
predator.
think.
The top
I thought it's the
predator
final.
we call it the top predator. إذا هو
top
الفاينل.
priority, exactly.
Yes, إذا
But
كان هو
eventually
الفاينل.
it will die, and
And
the
the matter
materials
will be
recycled into the.
recycled to
Yes,
the
yeah. ماشي.
But where's the? So I asked you.
Yeah.
I actually asked them that question because they were almost finished. So what's happening with the fox when the fox dies? Where's the matter going and where's the energy going? So
Decomposers, yes.
By decomposers, matter will be returned to the soil and to the air.
and where does it mostly go?
Mostly
To the soil.
as
To the soil, I would say.
لا air as carbon dioxide.
Yes.
That's another really. I mean, you have leaves too, right?
Decomposers,
So
why
if you have
decomposers?
fall, you get leaves piling up, and if you think about this, if you
Yes,
just
yes.
keep piling
Yes,
up leaves,
yes,
at
yes.
some point we would
Yes,
be.
yes, yes, you're right.
I mean, we would be swallowed by leaves. But what actually happens is the leaves get the decomposition, they get decomposed, and
To
most of
CO2.
that matter actually goes back up into the air. So that's part of the normal cycle of carbon being recycled into the air, and then it goes back into plants. So, so did anybody have any comments or questions? You're laughing, so you have any? The boss of everything. It's the boss of us right now. Yeah. So thank you for.
Thank you.
So give them a big hand. Thank you. It was. So let me move this because it gets in the way. So what I was very happy with is that they did a very good job in separating matter and energy and describing how it flowed through the ecosystem. And that's the kind of answer you want from your students. So through these type of investigations and activities, and you see it doesn't require equipment, it requires thinking and application of knowledge. Students need to understand what happens in the ecosystem. This is kind of the understanding students need by middle school. So, yes.
We usually introduce this food chain for grade 1 and 2 and also 3. Now I have realized that we cannot give a small picture of the subject. So what is your opinion of giving or to starting with indicating those points, energy transfer or energy exchange for grade 1 and 2 and 3?
You ask a really good question. So what she is saying is we're introducing this with young kids. So I think to a certain level of detail we can, but we cannot talk about energy and matter in detail like we do here. Because to do that, they need to understand much more about energy and matter than they know in second grade. And in fact, in high school, we go even further because in high school, we actually want to understand in detail the chemical reactions that take place in all these transformations. So we need to be, I think what happens in elementary school is much more descriptive, and we're moving towards an understanding of what happens to the matter and energy in middle school. But I think you came to a very important realization with that. So thank you for sharing that. So what I would like you to do now is want to give you a moment to individually write down in your journal one thing that you took away from this workshop that you could use in your classroom. Or if you're not a classroom teacher, you work with other teachers, that you could use with other teachers. So write that down for yourself because it's a good way to remember. Okay, so somebody willing to share an idea that they wrote down? Yeah. So.
I'm definitely going to add more observation exercises in the classroom, like the one you did.
So adding more observation exercises. So like with the match, so that we are clear on what are we observing before we go into explanation. So good. Yes.
Principles of mass and energy flows can be applied in a wide range of scientific disciplines, not just physics, chemistry, biology, ecology, blah, blah.
So great. So this idea of matter and energy flows is not just in ecosystems. I mean, it's a focus in ecosystems, but yesterday I did an activity with ice in a cup with water, and we have the same matter and energy flows that we can think about. In fact, they exist everywhere. Everywhere, in any topic. It's not just chemistry, it's not just physics, it's also true in earth science. You want to share?
The most important thing I have learned here is it's not important to go to the lab and have such complex and complicated apparatus to do an experiment. You have used only a match to demonstrate many things, observations and explanation. That this was wonderful. But this is the idea I will take to my class.
Yes, and I'm so glad that you say this, because you have to understand that people want to make money. So we have companies that will produce things, they want to sell it to you. And I'm not saying we never need them, but very often we can make science so simple. Also, if we make science and do things that relate to what students know in everyday life, it's so much more powerful. Like cups with water and ice cubes. Everybody has that. It doesn't cost money. A match, there are matches. I mean, people smoke enough, so there's matches around. So we can do this. So it can be very simple. Is anybody else who wants to share? So these are the presentations I did. I listed them because my understanding is that the slides will be posted on the website. So if you're interested in the other presentations that I did, there's one on Friday, Saturday, and Sunday. Just look for my name, and there should be slides there. I want to thank you for being here, the last session of the day, and you already shared some of the things you're taking away, so that's my purpose. So thank you for being here, and have a safe trip back home.